Good evening, everyone. My name is Ananya Pandey, and today I'm going to give a demonstration and presentation on one of the topic of computer vision, that is multimodal sentiment analysis using deep learning for the ELC activity, which is held in Thapar Institute of Engineering Technology. So before directly jumping on the demonstration of this particular topic, firstly I'm going to give a crisp idea about what actually is sentiment analysis and why we have switched to multimodal sentiment analysis. Then we will discuss about certain scenarios or strategies to conduct this research, and then we will go to the demonstration. Okay, so before directly jumping to what exactly is multimodal sentiment analysis, firstly I'm going to tell you what exactly is sentiment analysis. So in simple words, we can say that sentiment analysis is nothing but a procedure which is used to determine if a piece of a text is positive, negative, or neutral. So suppose here we are given three examples, three texts, okay, in which the very first text is my experience so far has been fantastic. So we are clearly able to get to know that this statement is nothing but signifies a positive sentiment. Similarly, we have other two examples for the neutral and negative sentiment as well. So this is exactly is what sentiment analysis using text based modality. Now the question arises, why multimodal? So here I have given two examples of multimodal post. In the very first example, if we consider only the image modality and ignores the caption modality, or we can say the text modality, then we are not able to get the actual sentiment related to this multimodal post if we consider only the image modality, because it is not clear whether it is a positive, negative, or neutral sentiment. But if we consider the caption modality as well along with this image, then we are able to get to know that this entire multimodal post signifies a negative sentiment, because if we read the caption, it basically signifies that the overall experience with this phone is not satisfactory because the build and the design quality was too low, so it is a negative sentiment. Similarly, in the second example, if we consider only the text modality and ignores the image modality, then we are able to get the sentiment as positive, because the caption is a sweater lover is excited for a sweater season. But actually it is not a positive sentiment, it is a sarcastic statement which is written like a positive sentiment. Okay, so if we consider the image along with this caption for this entire multimodal post, then we are able to get it that it is a sarcastic statement, it is not a positive sentiment. So this the sentiment of this entire multimodal post is a negative sentiment. Okay, so so why we need multiple modalities? Because if a model confuse or is not able to get the actual sentiment along according to one modality, then it is able to detect the actual sentiment with the help of the other next modality which is available. Either it can be audio or images or video. So here I am dealing with only two modalities, that is captions and images, which is also known as visual caption sentiment recognition. Okay, so what are the multiple modalities which on which we can work? So we can work on images, videos, audios, and text. So these are the four different types of modalities on which we can work. Now, how many combinations of modalities can be there according to it? So we have different types of modalities. We have unimodal models as well, or multimodal. In unimodal, we can work on single modalities like only on text, only on audio, only on video, or visual, we can say. In multimodal, we have bimodal and trimodal. In bimodal, we have binary combinations or two combinations, such as text and visual, text and audio, or visual and audio. And in trimodal, we have three types of modalities, the combination of three types of modalities, that is text, visual, and acoustic. Acoustic means the audio only. Okay, so these are different types of modalities or the combination on which we can work. Now, what is the motivation behind this topic? Why we need this multimodal? See, nowadays there are ample number of social media platforms, and on these platforms the comments, or we can say the data, is available in multiple formats, not only in the text. Because nowadays if we see that if someone do comment on some particular post either on LinkedIn, or we can say Instagram, or something like YouTube. So on that, the comments which we are reading, it does not contains only the caption modality nowadays, because it contains emojis as well, which is nothing but a visual modality. So nowadays the comments also a combination of multiple modalities. So now, and active users are also increasing on these social media platforms nowadays. Okay, so this is the graph which is showing that year by year the active users are increasing, and the data format is also becoming to multiple formats. So we need a system, a robust system, which can detect these multiple modalities for different applications, and one of the application for this is sentiment recognition, which is very, very useful. Okay, now what are the advantages for this multimodal sentiment analysis? The very first is we can have the richer context understanding. Okay, we can have more refined, fine-grained understanding of the multimodal post if we are having multiple modalities. Second thing is we can able to detect the sarcasm as well. Okay, and there would be a possibility of improved accuracy. This is very sure, because if we are model is confused with the help of one modality, it can detect with the help of another modality the right sentiment. So obviously accuracy will get improved, system will get more robust, and we have ample number of applications on which this can be used. Okay, now one motivation is also that till 2021, or we can say around 2022, what I find out that on unimodal sentiment analysis a large amount of research work has been done, and but there is a scope right now, there is a scope to work in the field of multimodal sentiment analysis. Okay, there is a large scope of accuracy to improve the accuracy and the results, and we can also give the benchmark data set for this particular field. So we have ample number of research work in the case of unimodal sentiment analysis, but we have limited number of research work in multimodal sentiment analysis. So there is a large scope to work upon this field. So this is also one of the major motivation behind this topic. Okay, so what are the research gap in this? So prediction of emojis using multiple modalities is less explored. Okay, multimodal sentiment analysis strategies are computationally expensive, so we can develop a model which is less computationally expensive. How? By decreasing the number of trainable parameters. So we would have to basically develop a model which is taking less number of trainable parameters, and there is a lack of effective sarcasm detection approaches as well. Okay, and there are limited number of application based research, and this is also a very good research area. And the last is there is no multilingual data sets available for multimodal sentiment analysis. This is a very less explored area on which we can work upon. So I am giving these research gaps so that student can explore these research area and start doing the work in this field as well. Okay, now this is a general architecture, how we basically define the architecture for multimodal analysis. So here if we are dealing with three modalities, though, so what we actually do is, if we are having three modalities, we need three encoders, one for the visual modality, one for the textual modality, and one for the audio modality. And after using these encoders for each of the separate modalities, we get three different feature vectors, and finally we fuse these three feature vectors to get this actual sentiment of a multimodal post. So this is the general architecture behind a multimodal sentiment analysis. Okay, now what we have to basically change while developing a model, we have to change the different encoders for visual, textual, and audio modality, and we can change the fusion strategies as well. So these are the two things which we have to change in general for developing an architecture. Okay, so in today's demonstration what I have done is, I have taken an MVSS single data set in which we have two modalities, that is visual and caption, and I am using a visual encoder of resonate 50, and for textual encoder I am using BERT uncased base model, and for the fusion strategies I am going to take a cross attention gated mechanism. Okay, so by applying all these different techniques and architectures, I'm going to basically implement this multimodal architecture for prediction of sentiment either as positive, negative and neutral. Okay, now fusion strategies, we have different fusion strategies, like we can suppose we can concatenate the two feature vectors. Okay, concatenation basically means join the features side by side. We can also add both the features. We can do element wise multiplication as well. We can do averaging as well. Attention fusion is also available. But for today's demonstration, what I'm going to implement is the gated fusion. Why? Because it learns much to take how much to take from each of the separate modality, okay, which is important. So it is focusing on the relevant information by while ignoring the rest of them. So it has some kind of intelligence as compared to the other fusion operations or approaches. So I have dealt with gated fusion. Okay, so this is the proposed architecture which I am using today for the text encoder. What I am done is, I am doing is, I take the input text, extract the features using BERT, okay, then project this to hidden dimension of 512. Again, image encoder takes the input image, it extracts the features using resonate 50, and again it is project to the hidden dimension of 5112. Why I am projecting? So that the text feature vector and the image feature vector will have the same dimension for the fusion process. Okay, and after that the third step is multimodal fusion. In this, what I am doing is, firstly I am uh, dealing with the cross attention mechanism, which basically what it does is, it takes the relevant information from the images and it append that to the text, and after that it applies the gated mechanism. The equation for the gate is g into cross plus 1 minus g into image fit. So cross is nothing but the text or the refined text, so g is nothing but the weights. So gating mechanism basically gives the weightage to image and text modalities by intelligence. Okay, by, so we are going to see the demonstration of this entire architecture now. So this is the data set. Those total number of samples in the data set are 4,869, out of which 1731 are positive, 1921 are neutral and 1217 are negative. Okay, these are the some samples I have taken to show you, and these are the results which I am getting after running for 10 epochs. Okay, so let's directly jump to the demonstration now. So I'm running it on Google Colab. So firstly, what I have done is, in my drive I have the zip file of this data set. So I am connecting my drive, Google Colab, with the drive. For that, firstly what I'm doing is, I'm basically mounting my drive. Okay, so let's mount the drive. Okay, okay, it's mounted. Now this command is used to install the tools which is needed for AI and machine learning on your computer. So I'm installing the tools, I'm running this command. And before switching directly to the architecture, firstly I have to import all the required libraries, okay, and the training configuration as well. I'm defining the training configuration, like how much epoch I have to run this model, okay, and other scenarios as well, like what are the optimizers I'm using, right? What are the BERT model I'm using? What is the hidden dimension which I'm using? What is the dropout layers? So I'm dropping out 0.3. Okay, what is the batch size? All these configuration I'm defining in this, along with the important libraries for importing. Okay, so here right now I'm running it for only 2 epochs, but because it will take time, so I've edited for 2 epochs only. So I'm running it for 2 epochs. Okay, so basically what here seed is equals to 42 means. So it makes sure that the program gives the same results every time if I run the program. So it is nothing but it initialize the deterministic random seeds across the libraries for reproducibility. Okay, now his zip path is equals to something path is given. So basically this path is the path where my data set is available in my drive. So this is the path which I have given from my drive because it is the path of the data set. Okay, now the model which I am using is BERT model, BERT base uncased. Okay, the maximum text length which I am using is 128. Okay, so why I'm using a fixed length, because all input will be of same size, so our model will be more stable and fast. And image size I'm using 224 and hidden dimension of 5112. Why hidden dimension of 5112? Because when we pass it it is a basic common sense. If you are taking a different encoder for the text and one different encoder for the image, then we will get the two feature vectors of two different dimensions. So in order to have the same dimensions, what I'm doing is I'm taking a hidden dimension of 512. So let's go ahead, then you are able to get to know how this these two feature vectors are converted into 5112. I'll let you know how this is done. Now dropout of 0.3 is taken. This is a regularization technique, you can say. Number of classes we are having is 3: negative, neutral and positive. Negative is for 0, neutral is for 1 and positive is equals to 2. Now best size we are taking as 16. Number of epochs right now I am running for 2. This is the learning rate, weight decay, and the test size and the validation size is 15%. Okay, so these are the configurations which I am dealing with. Now what I'm doing is, since we are having a zip file in my drive, so I'm unzipping it. Okay, so I'm extracting the zip here. So this code is first extract the data set if it's not already extracted. Okay, if it is already extracted, so no problem. So it is written in loop that if it is extracted, is already extracted, nothing we have to do. But if it is not extracted, then this code is for extracting the zip. Okay, then it automatically finds the label file and data folder, so the model knows where the data is located. So it is nothing but for extracting the entire data set and to know the where the folder is available. Now let's come to the next cell. So here what I'm doing is, so this code reads the label file, extract the valid sentiment levels for each levels and matches each sample with its corresponding image and text file, and finally creates a clean dataset containing the complete image text pairs. Okay, so this is basically after cleaning, what I'm getting is we are getting a total of 4869 samples, out of which INNA were neutral 1921, 1731 were positive and 1217s are negative. Okay, so the data type of this is integer 64. Now in this, what in the next cell what I am doing is I am plotting this few samples, random samples from the data set, how these samples are looking, how these multimodal samples are looking. So for along with each image we are having a particular caption. Okay, so these are three classes. So we have three classes for each of the separate classes. I have shown three different samples from MVSA dataset. Okay, and I've also visualizes the class distribution as well, how many negative samples are there, neutral and positive. Now data loaders. So basically this code prepares the data for AI model that understand both text and images. It cleans the text, convert into numbers using BERT and process the image so that model can learn from them. Finally, it organizes the data into batches for training, testing and validation. So basically, firstly here what I am doing is we are finding the image mean and image standard deviation. Why? Because for all the images we are normalizing all the images to a one particular scale. Okay, on the same scale, so the model will be more will learn more efficiently, right? And here what I am doing is we are doing certain transformations on the training set. Why? Because so in training we slightly modify the images like cropping, flipping and changing colors to help the model learn better and become more robust. Okay, because it can learn several different patterns. It can it is able to learn image which can be cropped, which is also which is flipped or changed the colors. So our model will be more robust. And for validation we have done no such changes, we have done just the scaling only. Okay, now for text what we have done is, so text is what text is nothing but the alphabet. So our system or computer does not learn from the alphabet, so we have to convert into tokens, or we can say we have to do the vectorization of those text. For that we are doing what we have taken is, we have taken the BERT encoder. Okay, so if you know that a BERT encoder is nothing but it takes the BERT tokenizer, tokenize the words or the text at sub-word level. If you go to the documentation of BERT from PyTorch, relate to if you read those documentation, then you will get to know that the tokenization is done at sub-word level. Okay, so here we are tokenizing the text into using BERT tokenizer. So our entire text or each caption is converted into the numbers. Okay, so here this has been done. Now this is the actual implementation of the model. So if you see that here we have 3 steps. The very first step is we are creating a text encoder. So this is the text encoder till here. So here what we are using is, we are using a uh, BERT base uncased model. Okay, so this is the BERT base uncased model or encoder. So if you read the documentation of the BERT base uncased encoder model, in that we get a dimension or a feature vector of 768 dimension. Okay, now after getting this feature vector, what we are doing is we are passing this CLS, or you can say the feature vector, to a self projection layer. If you see why, because if you know that in the very first cell, what I have done is, I have initialized some few configuration. In that I have also initialized the hidden dimension as 512. So in this model creation also, what I am doing is, after getting a feature vector of 768 dimension, I am basically self projecting it to a hidden dimension of 512. Similarly, for the image encoder, what I have used is, I have used resonate 50. After getting uh, so in this we are getting a feature vector of 2048. So why we are using this? See, here we are getting a hidden dimension of 768 from the text encoder, and here I am getting a hidden dimension of 2048 from the image encoder. So these two dimensions are different, and we have to fuse these two dimensions, and these two dimensions are not equal, they are different. So for fusion we need same dimensions. So for that same dimension we have to use the hidden dimension, which is 512. Okay, so that's why, to convert these feature vectors into same dimension, we are basically uh, sending these feature vector to a linear projection layer. So this is a linear projection layer, this is a linear projection layer for the image. Okay, after that, after these two lines, what it does is, image feature vector will also convert into 512, and a text feature vector will also convert into 512 dimension. After that we are implementing the fusion module. So this is the fusion module. So basically in fusion module what we do is, we apply the cross attention. So this is a multi-head attention with 8 heads. Okay, and after applying the multi-head attention, we are calculating the gated scores. So this is the gate score, G is the gate score. So G is nothing but the weight. So cross is nothing but the refined text. So G is the weight to the text modality, that is cross, and 1 minus G is the another weight for the image modality. Okay, after during training these g values will get changed for different samples, and finally we are fusing these two vectors, feature vectors, after linear projection head, and finally we have built our model. So total number of parameters was this, and total out of these total number of trainable parameters are these. Okay, so I want to give a one idea behind this. If you want to basically create a or develop your model, you want to develop your model, then always try to develop your model in a lightweight situation. Lightweight means you have to always try to make a model which give more accuracy, and along with that it should be lightweighted. Lightweighted means it should have less number of trainable parameters. Why? Because if you want to deploy it in the future, then you are able to deploy it on the hardware as well. Because if you are having large number of trainable parameters, it is very problematic to switch to any hardware. Okay, now training setup. So after this I am going to train this model. Okay, so it is going to get trained. So here I'm only training for 2 epochs, but because it will take a long time, we have more number of samples. So why it is for 2 epochs, in the initial configuration only I have set up this for 2 epochs only. If you see 2 epochs, okay, that's why it is running for 2 epochs. Okay, and after these training, I'm plotting the training accuracy, weighted f1 and loss. So loss is going downward, so it is uh, going in the right direction. Accuracy is increasing, and weighted f1 is also increasing. Okay, so these are the, for 2 epochs, these are the final accuracy, weighted f1 and macro f1. So for each class I have find the precision recall f1 and the overall accuracy and average of all these as well. So this is for 2 epochs, it is I'm getting around 64. Are you getting my point? So if we increase the number of epochs, so for sure we'll able to get the results more accurate. Okay, so these are the confusion metrics. So these diagonal samples are the true predictions. So you can see these are the true predictions, and this is the code for deployment. This is the code for deployment if you want to deploy for any website or the web pages. Okay, and these are what this code selects few random test samples, and we have displayed the image and predicted labels, the true label and the confidence score, how well our model is working for to show that. So actually this is a multimodal post in which this is Merry Christmas in July, celebrate with us on 7/19 is the caption. True level was negative, predictive was positive. So this is 73%. Again, this is this was true was positive, predicted was positive. This is good prediction. Okay, so these are the predictions which our model has done. So this was neutral, predicted was also neutral. So result will get more accurate if we run for more number of epochs. So right now we have run it for 2 number of epochs only. Okay, so now apart from this, I have also made deployed this on one of these site which I have made for this multimodal sentiment analysis. This is has been made on Streamlit. Okay, so here I have saved the model, and basically we can predict if you want to try few number of samples on this. So suppose I have uploaded this image. I have uploaded this image from the computer itself. So if I upload this image and the caption along with this is this, and if it analyze the sentiment, so it is coming 84% negative. Why? Because this is the image and the caption along with this is feeling confused and sad, so it is negative. So probability for negative is more, that's why it is predicted as positive, sorry, negative sentiment. And if we change this post, right, the caption along with this is, I am excited for the tournament. Okay, let's analyze the sentiment. So it is positive. So our model is working fine, I guess. Into so here I have basically saved the details for 11 epochs. So according to it, it is basically giving the results. So how it is doing is, so this is a multi-model post. The image raw text was, I am excited for the tournament. Cleaned. Firstly is clean, and these are the training details basically, which we are getting the results in our model. Okay, so these are the final results. Best epoch for running after 11 epoch, we are getting a best result on 7. So we have done the early stopping mechanism, which is a regularization technique. Okay, so this is the idea behind multimodal sentiment analysis. Okay, so in basic architecture is what? Basic architecture is this only, which I have shown in the PPT. This is the architecture which we have used. We if you also want to try, then you just have to change this encoder. In place of but, you can customize your own text encoder. In case of image encoder, you can customize your own image encoder. Okay, in for multimodal fusion, you can customize your own fusion strategy, and finally you can predict the model. So these are the basic three steps. Suppose if you are dealing with three modalities, then you have to basically create three architectures for the image encoder, and finally you have to fuse all these feature vectors into a multi-modal model fusion architecture. Okay, and one thing you have to always be clear that you have, for before fusion, all the dimensions, either you are getting it from the text encoder or from the image encoder or from the audio encoder, all these feature vectors should be of same dimension. So for that, what we do is we basically pass the feature vectors to the linear projection layer and convert each and every feature vector in spite of any encoder, and convert into a hidden dimension, which can be anything, any user defined dimension, but it has to be equal for all the encoders, and after that you have to fuse it to the multimodal fusion strategy. Okay, so these are the basic, this is the basic idea. Okay, you can try it along with any complex architecture, and always make sure that try to build a model with less number of trainable parameters, so that you can, it would be easier for you to deploy it on any hardware platforms. Okay, so that's all for today. Okay, so thank you.
Good evening, everyone. I am Lavi Dhumeja, Assistant Professor at Department of Computer Science, Thapar Institute of Engineering and Technology. So, I am presenting my ELC activity on emotion detection using deep face. So, anyone can guess how the AI reads the emotion from images. So, basically, it's a practical guide through which emotions or facial expressions can be recognized using deep learning in computer vision. Emotion detection is a field of AI where machines are trained to recognize the human emotions from facial expressions. Humans basically can interpret the emotions naturally, but machines cannot do. Machines needs the data, algorithms, and learning part, or you can say that the training part. Okay, so this is basically the human computer interaction, where systems are interactive about or aware about the users. Next is how emotions are how what are the different types of emotions. So emotions are we can say that they are the psychological states that influence the behavior and communication, or you can say that these are the internal feelings that can be judged through external expressions or facial expressions. So in real life, a student look confused, teacher explains it's again. So basically it is applied in education, it is also applied in healthcare as well. So in case of deep learning and deep face library, which is built the emotion recognition using Python, utilizes the 6 different type of emotions, that is basically occurs in our real life, that can be the happiness, anger, fear, sadness, disgust and surprise. So machines basically lack the emotional intelligence, and we are trying to build this emotional intelligence into the machine. That is our main concept. So can the machines understand the emotions? Basically, machines cannot feel the emotions, but they can recognize the patterns associated with the emotions. If we talk about the computer vision is having only the numerical data, which is then converted into the pixels, and pixel is nothing. Basically, each image is having a matrix of pixel values, and these pixel values are learned from the large data sets. Deep learning utilizes these large array of pixels value from the large dataset to recognize the patterns, and if a deep learning model is having the more data, its accuracy is more. So if you are going to recognize through a deep learning model a smiling face, you have to show the thousands of smiling face to the deep learning model. Then deep learning model can recognize the pattern that how a smiling face look like. So that is what the deep learning or the computer vision models are doing. So basically machine don't understand itself, they predict based on the patterns that we are giving to the machine. So first and the foremost application is healthcare, where emotion detection can be applied, like in the mood detection. It helps us to recognize the mental health of or the mental health of patients. It helps us to recognize the students which are participating in an educational activity, like whether they are involved in that activity or not. Next is the behavioral analysis or threat detection system. So in case of threat detection system, we can also express the emotions of a particular intender, which can be the malware or the genuine user. So, what is the emotion detection? How it can be applied? So, basically, it is a three-stage pipeline which transforms a raw image into an emotion label using a pre-trained deep learning model. So, at the first step is to detect the face or locate the facial region in the image. So, initially, in the first step, uses the algorithms like Haar cascade and deep learning to detect the coordinates of the face, that is the region of the face. And after that, in the second step is to extract the features, that is identify the landmarks and appearance patterns. So appearance patterns could be the features that could be extracted by the CNN, like the eye shape, edges, mouth curvature, after that the facial symmetry. So basically initially what this library do, it initially detect the face from the image, and after that to extract the features from that detected face, they have to identify the landmarks and appearance pattern of that uh, uh, particularly detected face. After that, for classification, the model has to use the trained model. Sometimes we can also train the model if we have the multiple or the thousands of data sets we are having. And then after that, the probability is output. This is the classify the emotion. So how the emotions are classified is basically list out the probability that this emotion is having how much percent in this image. So this is the example workflow. Initially, images input, then face is found. If the face is found, then features are extracted and analyzed, then emotions are predicted from that extracted face. Okay, so Next is the type of emotions. The model is basically on the trained on label data set where each image is tagged with the emotion. So initially we can say that if our image is having the smiling or raised cheeks, we can label it like smiling face, we can label it happy. And if the image is having the furrowed brows and tight lips, then we can label it as angry. And if the image is having the raised eyebrows and dropped jaw, then we can label it as surprise. And if the image is having the down-turned mouth and drooping eyes, then we can label it as sad. And if image is having wide eyes, open mouth, it can be labeled as fear. And in case of relaxed and no expression, the label it can be labeled as neutral. So basically, the model learned from the examples, not from the rules. So initially the CNN automatically extract the features without manual programming. What does the concept lies in this deep face library? CNNs are the backbone of modern facial emotion detection library. They automatically learn the hierarchical visual features directly from the pixel data. So it applies the filters, detect the edges and textures. This is the part of the convolutional layer. After that, the convolution layer, pooling layer is used. Pooling layer is help us to reduce the dimensionality of the features and preserve only the features that are required. That is, the size of the features is reduced. It helps us to keep the important or the relevant features. And the last is the fully connected layer, which makes the final decision and returns the probability across different emotional classes. So basically CNN detects the edges, shapes and expressions, and after that the emotion. Moreover, no manual feature engineering is required here. All is embedded into a single pipeline, that is the detection, extraction and then classification. This is a single pipeline of all the three terms that is involved in this Python library of deepfakes. Next is what tools are utilized in this library. Basically, one is the deepface. So deepface is a high level Python library which wraps which utilizes the TensorFlow also. So basically the purpose or motive of this library is to create a single API, single line API, which can do the detection, verification and emotional analysis using a single step. Using a single step means only a single function is required to call, which does all the three tasks automatically. Next is the OpenCV. OpenCV, we are all familiar with the OpenCV, which is utilized for uh, visualization basically. So it is an industry standard library for image input, output and display. It handles the image loading, to draw the bounding box across the detected faces and overlay the text labels and render the final annotated images, final annotated outputs. So the first step in this is to analyze the image. In case of deep face, this is the deepface.analyze function in which the image that you want to detect, in which you want to detect the faces, you have to give the path here, or you have to write the action is equal to emotion, because this deep face can also recognize the gender of the image. So here we have to pass the argument emotion if we want to do the emotion detection, and after that the result is output in the analysis variable. So basically what happens internally, it loads and pre-process the input image, detect all the faces present in the frame. It runs the CNN interference on each detected face. It runs the after that it returns the emotion probabilities for each face. So AI simply hides the complexity. It is a simple code, and but there is a powerful processing. So each detected face is treated as an independent input. So in this case, suppose if a single face is detected, then listed returned with the one dict or one dictionary, And if the multiple faces are detected, then the your resulting variable is having the multiple faces, so you have to run the loop to process the each face separately. That is a list of dictionary. Next is to extract the dominant emotion. The model output the probability using softmax function, we know. So whatever the emotion is having the highest percentage or highest confidence, which is to be treated as a dominant emotion. Deep face computes the probability for each of the 6 emotion classes basically, and after that it will select the one as a dominant which is having the highest confidence from the image in which we have detected the faces. After that we have to with this code we can draw the face location and draw the results. With this cv2 dot rectangle we can draw the bounding boxes over the returned faces, and after that we can put the text with the label that which emotion is recognized. So let's have a look at a piece of code in which this function is applied basically. So initially, if we look at, you have to install the library pip install OpenCV Python deepface ultralytics. Ultralytics is used for the detection model. It is having all the detection model. Deepface is the library and OpenCV is for the image processing. So this pip install is utilized to install all these the required libraries. Okay. Now after that, whenever the libraries are installed, next CV2 is imported, and from the deep face we have imported the deep face, a particular function which we can use to utilize to use the deep face analyze function of the deep face. After that, from the ultralytics library, which is having the many of the object detection models, we have imported the YOLO object detection model, as it is a very fast object detection model and it can detect the many objects at a very fast pace. And from the YOLO model, we have chosen the YOLO V8 YOLO V8N dot pt, that is the pre-trained model. Basically pt is the extension that is of pre-trained model. So this model is assigned to the variable YOLO model. After that, the image that we are going to detect is assigned to a variable img. Now with this code we are detecting the boxes which is having the person class. Suppose the person class is assigned in the as a class label 0. So if there is a person in a particular image, then the bounding boxes of that person's images is assigned to this variable r. Okay. Now the persons are counted. How many persons are there in the image? In this given image, it has detected 14 persons. Basically, this is our image 272310. So this is our image and it has detected 14 persons in this image. So after that we are going to calculate the distance between the image to know that whether there is a social gathering. If there social gathering means if there are no more distance in the between the detected faces, then it can be the social gathering. it may be the crowd. Okay, so there can be the different type of the basically the situation at which you are going to guess the emotion of the person. So there is, this is, you can say that this is the context, in which context we are going to detect the emotions. Like this is the individual image, it is a small group, it is a social gathering, or it is a group or the spread out. So for this we have to calculate the average distance. Okay. So after that, after detecting the average distance, we have done the people count. Now from the deep face and import deep face, this is the analyze function basically, which utilizes the image and the action is equal to emotion. And analysis, all the analysis is stored in this analysis variable, and for each phase we have done the analysis, we have reiterated this analysis variable and recognized the emotion of the each phase. And after that the regions are also detected for each phase. Okay, and then we have drawn the bounding boxes, or text is assigned to each bounding boxes. Now the main thing is emotion scores. In this code, scores are assigned to different emotions. Okay, for this we have used the data frame library from the okay, and these are the listed emotions. Here the face is not recognized by the model, so that's why they have predicted as a sad. So 50% sad, 46% angry, 2% fear, and 6% neutral. Like, so in this case you can judge that the dominant emotion is sad. Okay,